Okay. Uh, so I've got 405, at least on my computer. So I'm going to get started here. Today is January the 8th. So we're in the second class. Again, nothing due specifically this week. Tutorial 1 has been released, and you can get started on it, and you can submit it, and you can finish it. You can't get help from the TAs to do it. Or you could if you use their email address. Next week, the tutorials, the office hours should all start. The both tutorials will be due next week. Neither of them are very long. Tutorial 2, I should release later this week along with assignment 1. Assignment 1 is basically done. I just want to give it a little bit of time to think about it and make sure that I'm happy with everything, and then reread it and try and find some mistakes, and then release it to you guys, and you guys will find the rest of the mistakes. So yeah, it is, I might actually do a short demonstration of sort of the thing you'll be building. We will be using the X11 windowing system. All right, it's more of a C library, and it's very low level. Right, it's basically, well, you set up a window and then you can draw on it rectangles and lines and things like that, but it doesn't have a GUI, right? I can't add a button, the same thing you might do in Java FX. I can't add a button or a text area or something like that. So what we're going to do is we're going to build those things, or at least that's the idea. Assignment 1 is going to be some very, very simple stuff, like draw some buttons on your window. All right, so X11 is not directly related to C++, but it is a nice way to demonstrate the power of adding abstractions to a language, right? We're going to take this really clunky thing and hopefully put a nice interface on it, and so you can make a nice, easy GUI. Now, that's a big if. If we complete this whole thing, it'll be nice because it'll be a nice thing. It's an actual library, right, that you could actually showcase and people might actually be impressed with instead of the usual toy stuff we do. That being said, it may not get to that stage, right? There's a whole bunch of things that could go wrong, and at some point we may decide to abandon it. We'll see. I'll try and judge the level of panic. I don't think it's too hard, but I'm not always the best judge of that. And also things like text areas are difficult in X11 because everything's got to be manually placed. There are ways to do that, so I don't know. We'll see what happens. Maybe I make you do that, or maybe I give you a little bit of code that sort of gets you halfway there. But yeah. All right, so that's basically the calendar. Any questions? All right, today I'm going to demonstrate another way. So each class, I said there's multiple ways you can set up your programming environment. So today I'm going to demonstrate OpenStack, walk through. For those of you who, for whatever reason, maybe the VM is just
Yeah. And then I was under the bumper.
Or you're running the Mac with the M series chips, so you can't use the VM. And so you can either run it natively, which I will help you out with if you want to, or you can run it through OpenStack. All right, so I'm not going to go over how to open your OpenStack account. If you Google Carleton OpenStack, you'll get to a nice web page. There's a bunch of 2-minute videos. It's quite easy to follow. Yeah. Yes. Yeah, that's fine. If you already have something set up, then this is not really for you, right? But it's up to you. Some people might want to play with OpenStack or whatever. If you have something that works, that's great. No. If you have the VM and you're happy with it, then you're kind of like, you're one of the lucky ones, right? And most of you are probably in that point. Some of you might have older computers though, and the VM is slow. And again, the Mac, you're forced with either running Clang, which is it's pretty good. It's not perfect. You still have some technical issues, or doing OpenStack. So I'm just going to demonstrate. Other questions? All right. So what is OpenStack? Well, you have to go to, you have to go set up your account. Yeah, same setup you use in 2401, absolutely. Should be fine. And we'll, anything that happens, we can troubleshoot. So yeah, so you set up an OpenStack account. It's going to set up a server. There's a server running here on campus. And then you're going to assign it an IP address, a public IP address. And then you're going to, well, you want to connect to the OpenStack instance now, right? So what I'm going to do is I'm going to open a terminal. This happens, well, we'll talk about which terminal this is in a second. So I want to open a terminal and I want to connect to that OpenStack instance. You don't have to. Sorry, yes, you do not have to use OpenStack. But for those of you who are using OpenStack, this is some information that might be useful, or you can try it if you like, because it is kind of convenient once you set it up. So I'm just going to briefly, this will be 5 minutes demonstration, nothing too long. So once you have it, you want to I have some one of my keys is stuck on, perhaps. Yeah, my shift key is stuck. All right, there we go. Okay, so once you set up your OpenStack, you set up a public IP address, you're going to SSH in like this. And if you're going to do this, I'm using the -X here. This is because I want to use the X11 server, right? The X11 windowing system. If you're not using that, you don't need the -X. You can just SSH in. The username is student. This is the public IP, right? So you can actually try and SSH in. The thing is, the first time you go in, it's going to ask for your password. You're going to enter student, and it's going to tell you have to change your password. So you're going to choose a new password, and then it's going to disconnect you, and then you can try again. You can just SSH in again. I'll enter my password. And voila, now I am actually in my terminal on my machine, but this is actually running on a different machine. And all right, so that's great. I can list the files. I can see that COMP2404B, we will add something beside that shortly, but let's go to documents. And you can see the assignment 1 solution, or at least the solution so far. Whoops. And then I can run it right from here, right? Just as if I'm there. So it presents this menu, and these marks are subject to change, so don't get too... but yeah, I can even open a window from there. In this case, I can open a window because this is an Ubuntu shell, right? This is the Windows subsystem for Linux running in Windows. And it has X11 client capabilities. So this code is opening a window on, it's running on a server somewhere else, but it's opening a window on my machine, right, with a few buttons. And then press enter to continue. I have a panel, I remove the panel, and then it updates, and then, yeah. So OpenStack, it's very viable. Again, if you have a working solution, you're good. You don't need to do this stuff. But if you want to try it, and some people I know are actually using it, and some people may want to use it rather than wrestle with whatever system. The recorded lecture be posted today? Yes. The other one, for some reason, I forgot to post. I just posted it before I got here. So the first lecture is now posted, and this lecture should be posted when I get back after class. Okay, so how do we edit the code? Well, you can use Vim if you're a Vim wizard, which I am not. Actually, let me get out of here. Let's just go to, but what I'm going to do is I'm going to click on this. So I'm going to, this is Visual Studio Code, and there's an extension, the SSH extension. And so I'm going to, whoops, I don't want to do that. I'm going to go here to the remote menu, and I'm going to add an SSH. And here you can see it's just asking for an SSH command, right? So I can do, well, I can just fake it. Student at Carleton, right? This is not real, but this is, if I had a DNS server and stuff like that, this could work. And then it's going to ask, well, where do you want to store this SSH configuration? And you just choose one of these. I choose this. This just means it's for my own username. This means it's for everyone on my computer. I can open the config file and look at it. There we go. Now, if I want to connect, this is not a valid link, but this is a valid link. So I can say, well, let's connect. It's going to ask for my password. And yeah, now VS Code is connected to the same thing, like through SSH. I haven't opened a folder yet. So I'm going to open a folder. Actually, let's just open student, and we'll add to that. So I'm going to open the student directory. It's going to ask for my password one more time. And yeah, there's the big student directory. I can make, don't really want it there, but 2404A, and I can hopefully try and move this out. And it won't let me. So I can do it from the command line, however. But yeah, so from here now I can start. Well, let's look at the previous. So this is code that exists on a server that I can edit in my VS Code, just as if it was on my machine. And then once I edit it, I can run it from this command line. Okay, and you can also open a terminal in VS Code. And so this all behaves as if it's a file system on my computer, but it's actually a file system across the network. The idea for the tests is I want you to write code. There will be written code no matter what. There might be multiple choice as well. Yes. Can we use the same virtual machine as? Yes. No, you don't need to do the OpenStack. This is all optional. Okay. All right. Questions? All right. So I'm going to use this setup today just for fun. Hopefully I can. What can I do here? I can make a directory. All right. Should show up here somewhere. There it is. And if I want to add files to it, I can go to this. So we were working on the introduction, so I'll add that. It gets copied in automatically, just, sending text over the wire. And we will probably get to this as well. Don't add it in there. Yeah, there we go. Perfect. Right. So I can pull those. And if I want to, like, if I do some work and I want to bring them back to my machine, I can right click and do download. Right. So very, very easy. Okay. So last class we left off talking about makefiles. Right. So we had a little program, this main And we compiled it. And from main, we called the function foo. And this function is defined in foo.h, but we don't include the source code, right? So in our make file, we compile main into an object file, main.o. And then we compile a separate object file, foo.o, from the foo.cc. Foo.cc contains the implementation of the foo function, along with all the context that I need so that the compiler can compile it. Once I have those two object files, I can link them together, right? So I make an executable called main, and I just link those two pre-compiled files together. And all of this happens automatically. And so yeah, if I'm here. And I run make. Well, for whatever reason, it sees that main.o and foo.o were up to date, but we should recompile this main. And I imagine it has something to do with the difference between the clock on my computer and the clock on OpenStack. But yeah, and then if I go in, if I run make again, it says main is up to date, right? And I'm running make, and when I just run make, what it does is it looks through here and it just runs the first command that it finds. In this case, it's main, and then it runs whatever other commands it needs to do to make main, but that's it. I can explicitly ask it to run certain commands in my make file by saying, for instance, make main. Says the same message, main is up to date. I could say make main.o. It says main.o is up to date, right? So, so what I can do is oftentimes or sometimes make files will have multiple executables that they build. And what I want is to make them all. So we make an all command. Now the all command, all I'm going to do, there's no commands that get run. There's no compilation commands. I'm just going to list all of the dependencies, which is all of the things that I want compiled. So if I run all, I want it to look at every single executable that I want to build and check to make sure to see if I should recompile it and recompile all of them. So I only have one executable I want to build here, so I'm just going to list that one. But often you might see as a compilation instruction, please, run make all. And if I do that, then it'll double check this stuff, right? And if I say make a change to foo.cc, and then I run make all, well, it recompiles foo.cc, and then since foo.o is changed, it relinks it into my executable. Right, so the all command works just as well. So, right, these are the main commands that I use to build my executable. But in addition to that, on my make file, there's often an all command, and in addition to that, there's often a clean command. Clean has no dependencies because every time I call clean, I want it to run. And what I'm going to do is I'm going to remove basically all binaries. So all executables, in this case main, and all object files. And start from scratch, right? Because sometimes, again, when you're using virtual machines and things like that, where the clocks are different, sometimes the fact that the make file checks all these dependencies just doesn't work, right? Because I recompiled on my computer over here, and then I came to school and I accessed it, and the clock is different, and it thinks that it needs to recompile it again, or maybe it thinks it doesn't. So yeah, so make clean. If I want to, recompile everything from scratch. All right. Instead of listing all of these explicitly, I can use the wildcard here, the star.o. So just remove every single object file that you find along with the main executable. And probably the dash F just to be sure. Now, when I run remove from the command line, sometimes I get a like, are you sure? Right? Yes or no. And so you put yes, but if you put the dash F, it's a force, right? And I think it is, off the top of my head, I don't know the reason. It's probably something to do with permissions, whether you actually have permission or I don't know. I'm not exactly sure, but I've never seen it happen running a makefile. But I mean, that's, you know, whatever. I've not seen every makefile in every system. So, so yeah, dash F just to be safe. And that's it. This is basically a complete makefile, right? We're going to talk a little bit about variables and things like that once we get to assignment 2. So how we can take this and like make it simpler. But for assignment 1, I would prefer you to like hand code all this, just so that you know you get a feel for what it's actually doing. If you just jump right into the variables right away, then sometimes you can miss like what's actually happening, which means that it's going to be difficult to debug later. All right. Questions? Yeah. Use wildcard in main? This thing, yeah. Down here? Oh. That's a good question. That's not typically what I mean, I don't know. I feel like this is almost a bad idea, but let's try it. I've literally, now modern computers are pretty robust, but playing with makefiles, I have literally had to reboot my computer because I put an infinite loop in there somewhere and it trashed my, like everything was locked up and I couldn't do anything. Yeah, let's see what happens. Well, undefined reference to main. On this call. Okay. Yeah, so I guess not. I'm not sure. Maybe there's a way to force it to do it, but I'm not even exactly sure what that is asking the makefile to do. Because the wildcard, like this is just this gets run on the command line. It's clear what a wildcard is there, but like up here, I'm not sure if it has any meaning at all. Maybe not. All right. Other questions? Okay. Think. I included so yeah, this is your complete makefile. Basically, when you make one, it should look something like this. I did have a little bit on large language models. Probably you've been lectured on large language models before. It might be time to, it's not even not even very well put, but let's just talk a little bit about a large language model is and what it can do. And what it's good at and what it's not good at. And I'll say, because this came up last class, well, the last section, is that I don't believe that every time there's an advance in technology, there's a bunch of people who are afraid that people are going to lose jobs, and some people do, but a whole bunch of other jobs are created. And I think that pattern is going to be here. This idea that a large language model can write code. Well, sure, it can write code that it finds, that it's found on the internet that already exists. It's very good at that, right? So you want to write a linked list, you want to even write a vector, like all that code is publicly available. It'll do that flawlessly. But if you want to make something new, right? And if you're being employed to write programs, generally speaking, they want you to create something new. If the thing that they want to create already exists, they could just buy it, right? Or steal it or whatever. So generally, you're going to create something new. So you're going to create something with a pattern that T has never seen before. Now, it's going to attempt to fill in the blanks from the closest things it sees, but it has no way to evaluate whether it's correct, right? That's the thing about, maybe you know this and maybe, maybe, I don't know, you guys are all smart people, but like a lot of people seem to like miss this thing. Like a large language model cannot evaluate whether what it's telling you is correct. Even mathematically, it can't. Like it's not as a sound deducer as a simple calculator. It can just reproduce patterns that it finds on the internet. And it turns out that actually works pretty well for a lot of things. And what it's very good at is, for instance, like I can't tell you, I know a whole bunch of languages. You ask me to open a file and I'll be just like, I'll have to look it up. Like I can't remember how to open a file ever in any language whatsoever. So something like ChatGPT is very good at stuff like that, right? I just ask it to say, how do I open a file in Python? Like open a file, a CSV file, and read it in. And it gives me a bunch of code that works perfectly. And it's just like, great. Like it used to be, I'd have to Google that, and I would go to Stack Overflow, and I would copy and paste that code, and maybe I understand all of it, or maybe I just understand some of it, but I understand enough that I can integrate it and make use of it. And now we can do that just faster. So it's very, very good at that. And in terms of like the X11 libraries, again, these are kind of like esoteric. There's a bunch of like little details you have to fill in and stuff. It's hard to remember all that stuff off the top of your head. Like this is a good use for a large language model. Hey, how do I open a window, right? How do I close a window? Like how do I free the memory? Stuff like that. These are good questions to ask it. But again, once it starts to get complicated, it has no way to evaluate if the thing it's telling you is correct, right? So it's just going to try and match a bunch of patterns, and it's going to put all these things together. And I've seen like, I mean, it's getting better and better, but again, these are on applications that have already been written. So when you're trying to write something original, there is still a role for the developer, right? You still need somebody who knows how to program. A, just to write the code. B, if you want to, like, I use Copilot and I have to turn it off sometimes because it's so dumb. It just suggests the dumbest stuff. It's very good at extending a pattern. So if I write a test and then I want 20 of those, it'll do that, and it'll do that perfectly. But I'm trying to do something original, like I'm trying to think around this problem and how to solve it. I have to turn it off because it's so stupid. Like it just doesn't know how to do it. So yeah. That's my little spiel anyway, just to sort of, also like, I could be wrong. So I don't think anybody's developer job is in trouble. In the short term, there's a lull in the industry right now, right? But I think it'll bounce back. And it'll be just, people will just develop just faster. Like the same thing that Stack Overflow did and the same thing that Google did. We're just getting a little bit faster. That's what I believe also, but I could be wrong, right? So take that with a grain of salt. Anyway, questions? All right. Okay, so I want to give you guys some background because when we talk about C and C++, we're talking about like we're running close to the metal, right? So what does that mean? There used to be a computer organization course here, or I think there might have been multiple computer organization courses, which means that like, how do I build a CPU? And you'd be surprised at how simple it is, right? These things are not complicated, but what they are is very fast. And then you write like clever algorithms on top of it, and all of a sudden you have like Skynet, right? So yeah. I want to give you a little bit of a mental model. This is going to be this is going to be the 10-cent version of computer architecture or like computer organization. Just so that when we talk about pointers, we talk about memory, we talk about the stack and the heap, you have a slightly more accurate idea of what's happened, okay? If you're in my 2401, maybe even if you're in Connor's 2401, you may have seen something similar to this last semester. So this is a bit of a repeat, but I like it. So we're going to talk about CPU architecture, memory layout, and then the pointers. I think I removed that. But CPUs are surprisingly simple. I've been yeah, well, let's talk about it. It looks something like this. So we have a control unit, logic math unit, and some registers and some RAM. And well, the RAM is just memory. It just stores stuff. The registers also just memory. The control unit reads in the instructions, decodes them, runs them so that something happens. I compare two things, I add two things, and then it loads the next instruction from somewhere in memory and keeps doing that over and over again. The logic math unit, basically, if I can add two numbers, I get a lot of stuff for free from that, right? Like, so the very simplest CPU, I just take two however many bit numbers and add them together. And then, well, I actually get subtraction for free because I just use the two's complement, right? And then, so if I add a negative number to a positive number, it's like I'm subtracting them. And I can easily convert from the regular notation to two's complement, so I can negate a number pretty easily. And then I get multiplication for free, right? Because if I can add two numbers, well, I can add 3 to itself 4 times, right? And then that's just 3 times 4. So I can just loop and just keep adding the same number however many times. And I get integer division for free also, because that's just subtraction until I reach a negative number. So the very simplest CPU you can build is remarkably simple. And then on top of that, you're going to build these clever algorithms that can do these complicated things. Now, modern day CPUs bake all of that into the hardware so that they run really, really fast. But technically, the simplest CPU is as powerful as the modern CPU. It's just a lot slower, right? It can solve the same set of problems. All right. So, yeah. Add, compare numbers, make decisions based on logical output, right? I can, for instance, check to see if some memory location is equal to 0. And if I could do that, then I can test to see if two numbers are equal, right? I could just subtract them and then see if the result is 0. So yeah, there's a lot of things you could do with just an adding unit, and you're almost at a fully fledged CPU. All right, so I think I talked about all of this. So here is another version of our CPU. What we're going to talk about is, well, we talk about C++ as a compiled language, and it compiles into object code and executables, and this is machine language that can be read by your CPU. What do we actually mean by that? Well, we have our RAM, and there's a bunch of memory, and so we compile our program. And when we compile our program, so now this memory that was previously empty gets our machine code. Now, machine code is just numbers, but you can sort of make a set of instructions that correspond to those numbers, right? So this is called assembly. So I have some number here, but I know that this instruction loads the number from location 6. So in assembly language, we call that load 6. And then I have another instruction here that adds whatever's in the accumulator to location 7. And so in assembly language, we call that add 7, right? So there's a very nice one-to-one, pretty close to one-to-one conversion from machine language to assembly language, right? So that's why assembly is like, well, when we compile C++, you can actually compile and read the assembly code. And that sort of gives you an idea of what it compiled into and what your CPU is actually doing. All right. Questions so far? Okay, so we're going to do the fetch, decode, execute cycle. We're just going to go through, this is a program, a small program we've compiled. We're going to see how it runs on our CPU. So we have an instruction pointer. So these are just all 3 are memory locations, but this stores the next instruction. And this is just an accumulator. We can use it to add stuff to. So fetch, so we compile it, we load it in, the instruction pointer is set to the first instruction, which is at location 0. So we load in that first instruction. We copy in the instruction at location 0. So load 6 gets copied from here to here. And then we enter the decode cycle. And what that does is it takes the instruction and, well, modern CPUs are very complicated, so it might break it down into like these 4 bits go over here and these ones go over here, depending on what the type of instruction is. So here we're deciding what exactly this instruction does. And in this case, we know that it loads the value at location 6. The value at location 6 is set to 1. And so that gets copied into the accumulator. All right. Our instruction pointer, as soon as we read the instruction, we incremented it. So now when we go to the next step, we've done the execute. We're going back to the fetch. We're going to look at the instruction pointer. We're going to read the instruction at that memory location and copy it into the instruction register. So add 7 gets copied into the instruction register. The next step is the decode. To decode, it says, well, add what is in the value that's in location 7 into the accumulator. Right? So when we decode it, we figure out what we're doing. And then we're going to execute it. And when we execute it, we add 1 to 1 and we get 2. The instruction pointer was incremented right after we used it. So now we read in from memory address 2. It says store 6. We copy that into the instruction register. We decode it. We say that, oh, we want to write whatever's in the accumulator to memory location 6. So yeah, we take this value and we write it to location 6. And so now 2 is in location 6. The instruction pointer points to 3. And so we go to the next fetch. We fetch, it says jump 1. Copy that in, we decode it. It says, I want to run the next instruction here at relocation 1. So I'm going to take my instruction pointer and I'm going to set it to 1. Right, so this is, yeah, and then I execute, I set the instruction pointer to 1, I fetch the next instruction at location 1, and I keep on going. Right, so this is a very short loop, just a few instructions, and it basically keeps on going forever, right? And this jump, so this if and else and while and all of those things don't actually exist in our compiled code. What we have is jump and conditional jumps, right? So jump if some register is equal to 0, which is why when, they first started writing programming languages, they had this command called goto, because goto corresponded to jump. But what they found is that it really made a mess of their code. So at some point, there was a huge campaign against the goto. And then you got, we figured out that, hey, we can write the same code just like using some nice control structures like if, then, else, and things like that. All right, so yeah, we keep going. And yeah, so this is the smallest assembly language program you've ever seen, right? But if you compile, you compile your C++ code, you can read the assembly language. But what this is this program. So I can write a program like this in a high-level language. I run the compiler turns it into this set of instructions, and then it copies it into memory. And then when I run it, I just load up the memory location of the first instruction and then just start going. That's it. So yeah, again, that's not just trying to give you a slightly more accurate view of how computers actually work. Because we're going to talk about, I'm going to refer back to assembly language multiple times during the course and things like registers possibly as well. But any questions? Okay. All right. So, well, the other thing that happens when we compile a program and run it is that a bunch of memory is allocated for us. So we looked very generally at the RAM, right? A RAM is just a big, long piece of memory. But we're going to divide that up into a bunch of different sections to be used for, is there an instance of our class on the OpenStack? There should be, right? You have to update your SCS account, right? So if you go to Carleton OpenStack, there'll be instructions there to do that. If you don't update it, it doesn't know you're in this class. So yeah, when we compile a program and run it, 4 main areas of memory are allocated for our little program. Now this is a memory model, okay? So, and it used to be more or less correct. Now what actually happens behind the scenes is anybody's guess, because the hardware vendor can do whatever they like, right? So what generally happens is that there's not a memory model, there's a specification, right? So what we say is that for this language and this compiler, I should have X amount of stack space. I should have some space for global variables. And when I ask to malloc or new some memory, you should be able to give me like at least this much before things crash, right? So there's something like that. There's just, this is what should happen. And then when people build computers, they figure out how exactly it happens, right? So this is a model, but it's, you know, a decent one. It'll give you a good idea of things that do actually happen, like stack smashing, right? Or, right? So we'll talk about that in a second. So anyway, you get 4 areas of memory. You get the function call stack, the data segment, code segment, text segment, and the heap. Data segment contains global memory. So global variables, string literals, static variables, things like that, things that are going to last the entire lifetime of your program, go in the data segment. That is followed by the code segment or text segment. Let's talk about this. Assume this is the piece of memory that we've gotten. You know, the first command is jump to 17. This is where our code begins. So we have our data segment here. And this is where things like a string literal will go. So if I ever use the word Bob anywhere in my program in quotations like that, it will actually be stored in this data segment for the entire lifetime of my program. And then here is where the compiled code goes. So the code segment is generally speaking right next to the data segment. Again, this is a specification. This is a model. So it could be done differently. Mostly it's probably done like this. And so this is where all our compiled code goes. On the other side of the space that we were been given, traditionally has been the stack, right? So the stack grows in the opposite direction of where our program is. And if you read Marc Lanthier's notes, he puts the heap here. And the heap and the stack both grow from opposite sides of this piece of memory in opposite directions. But again, while this might be a useful model in some scenarios, I do not believe that this is accurate, right? Maybe there's some heap space allocated there, but I know for certain I can get more heap space than stack space, right? I can, if I put all of my data structures, if I take an array of longs of size 1 million, and I put that on my stack, I will probably get a seg fault, right? It'll just crash because my stack will take up all of this memory, and then it'll start to bump into my code segment. And so I get a seg fault, and it just says, "Nah, that's, you know, I don't know what you did, but it's wrong." On the other hand, I couldn't put an array of size 1 million longs on my heap, no problem. That'll work, right? So the idea that's in Marc Lanthier's notes, although a good model, is not accurate. You have a lot more flexibility in the size of your heap. You can always ask for more heap memory, whereas your stack, you're given a limited amount. And once you run out, you get, well, in C++, I believe you get, in Java, you get a stack overflow. All right. So yeah, the data segment, code, stack, and then I ask the operating system for extra memory by making a call to look or new, and it comes back. Maybe I I allocated a huge chunk, I need to array. It says, well, here's a memory location. I'm giving you this much memory. Here's the start of it. Go crazy, right? So the memory location here is like 0, 0. So I store that in one of my stack frames, and then I can access that memory on the heap and do whatever I want with it. And at some point, I can say, delete this, and it hands it back to the operating system. All right, questions? Okay. Okay, we'll talk a little bit more about these moving forward. I just wanted to give you a good foundation. All right, basic language features. Now we start very slow in this class, and I have to apologize. One semester I decided to skip all this because I'm like, you guys have taken, at least 3 languages right now, right? Like Python, C, Java. And you've seen all of this before, and I skipped it, and then I started getting a bunch of questions during class, right? So there is some repetition here, but sometimes repetition is good. For those of you who program a lot in your spare time and who are experts, like maybe this is going to be a little slow. But I know for myself as well, like there's a lot of concepts I saw multiple times and I was grateful for it because in the beginning you just kind of understand it and then you have more context. The next time you see it and you go, oh yeah. And then you make some more connections and things like that. So let's talk about the basic language features of C++. Well, first of all, no virtual machines, no interpreters, no garbage collection. Not even smart pointers, unless we make our own, maybe at the end of the semester. We're going to manage everything ourselves at a very low level. All right. So one of the biggest differences between C++ and other programs, aside from C++ is way complicated, or sorry, other languages, is the fact that it handles its own memory, right? That's actually kind of a rarity these days. And 90% of what makes C++ either work or not is this idea of like, well, you can do so much damage with memory, right? You can introduce memory leaks, you can run off the end of an array and access memory you're not supposed to. I can corrupt other variables. I can get the seg faults out of nowhere. There's a whole bunch of stuff that can go wrong. A short history of programming languages. We'll not go over all of this, but really all of this, I mean, aside from assembly. Assembly's still around. If you write compilers, you'll be writing assembly. But everything else is sort of fallen out of favor, right? Except for C. C is as popular as ever. So it's kind of interesting. Prolog scheme. C++ came around in 1980. It was C with classes, right? This may seem like a million years ago, I suppose. But in terms of technologies, this is all of these are very, very young. Objective-C, this predates Swift, right? So if you write programs in iOS, you'd write it in Objective-C. Java, 1995. So Java is quite new, relatively speaking. And then, of course, JavaScript, which is the mighty JavaScript, right? So important these days. And even PHP is still sticking around. I used to program in PHP, well, as a hobby, right? Just to help people out. I was making websites with PHP. Once upon a time, it was so popular, there was something called the lamp stack, right? Anybody know what a lamp stack is? You do, yeah? You want to try? Yeah. Maybe L is Linux, yeah. I mean, I can't remember. You got some? MySQL, yeah, that's the one. I was trying to think of what's the database one. But yeah, MySQL. Yeah. So yeah, lamp stack used to be very popular, and the P was PHP, but it was also, I think there was some other one that you could substitute. I don't know, I forget. Anyway. Which one of these is the most powerful? Well, it turns out they're all the same. When you get right down to it, right? They all run assembly code at some point. But more specifically, they're all Turing complete, which means the set of problems they can solve is the same for all of them. The difference is like how fast they run and what features are convenient in them. So otherwise, there's really no fundamental difference. All programming languages manipulate data. Some examples, so C++ has primitives, right? Some examples are int, float, double, char, bool. Bool is a new one from C. The other ones you've seen in C, along with short int, long int. Basically, there's not that many primitive data types, right? A char you could think of as an int. And if you want to use it as a character, it's just you look it up in a table, right? It's just a number. It's the table entry for that character. An int is just an int, obviously. Short is an int, long is an int. A float is floating point, and a double precision float is floating point. And then, I mean, Boolean is like a bit, but it's represented, it's 8, it's a byte, I believe, in C++. And then really that's it. You have like floating point and you have ints. At a fundamental level, I don't know what else there really is. I might be forgetting something, but I think that's it. On top of those, we can build aggregate classes. So structs and classes. You're familiar with structs? With a struct, I just take a piece of memory and I jam a bunch of primitives together, or primitives along with other structs or something like that. Right? I just put all of these pieces of data together in memory and I call that a struct. And in C++, it's largely the same. Yeah, it's just a piece of memory with a bunch of data in it. Now there's going to be methods associated with that data. So there's something built slightly more complicated than C, but in terms of memory, it's the exact same thing. We also have pointers. So pointer is just a memory address, specifically with a type, right? Because C++ is a type-safe language. All memory looks the same, so how do we know what type it is? How do we interpret it? And that is, well, we look at the variable type. So basically, we have some piece of memory that points at another piece of memory. And the one piece of memory has like a label, a type, and that tells the compiler how to interpret the bits that it finds at this other piece of memory. Right? So even a pointer says that, well, this is a memory address, so you should treat it like a memory address. Yes. So all variables have a name, how the compiler and the program identify it. They have a type. That's it's a strongly typed language, not like Java, or sorry, Java is strongly typed as well, not like JavaScript, not like Python. Those use duck typing. And I mean, you guys probably have more JavaScript experience than me at this point, since JavaScript has become super important to our degree and in general to get jobs and things like that. But like, what a nightmare sometimes a duck typing is. So I made an application in JavaScript, and so I wanted to draw something on the screen. So I had a number. It got converted. I accidentally appended it to a string. So it got converted to a string. And then that added to another number. So that's a string plus a number. So it converted the other number to a string and it appended them instead of adding them. Right? So instead of like 1,000 plus 1,000 equals 2,000, it was 1,000, append 1,000, and it's like a million or 10 million, 1,000. Right? So then I tried to draw the thing and it says, oh, you're trying to draw, so I'll convert it back to a number for you. And so now I drew the thing at like location 1 million way over here, and it was like, I could not find it because it started as a number, it ended as a number, and here, like for a brief second, it turned into a string. And so like I had to track down that like brief moment where it turned into a string, and I was like, I couldn't, it took me forever. So yeah, that's duck typing. That can't happen in C++. Everything has a type. And while that may seem like a pain, To me, it's not that big a deal because that's basically how I learned, but it does help us to debug better, right? That mistake would never have happened in C++. Each variable has an address, where in memory it's stored, and the value, of course. All right, so we manage our own memory. So which memory are we managing? Well, there's two places where we allocate memory for ourselves. So it's either the function call stack, which is fast and convenient, but temporary, right? So these are called temporary variables in a function. But at some level, like everything is attached to the function call stack. Or the heap. So it's slower to allocate, but it lasts until we call delete. So we can manage the lifetime of the heap better than the stack. However, it's slower, right? Because, well, I can ask for an int, right? And then I can ask for another int, and it says, sure, I'll give you one right beside it. And then I can ask for a third int, and it says, oh, great, I'll give you the next piece of memory. And then I say, well, I don't need the middle one anymore, so could you please delete this? And so the operating system does. And now the heap has to keep track of this piece of memory and this piece of memory and remember that this one is empty, right? And then if I allocate a new int later, it can come back and fill that. But in the meantime, it has to keep track of all this stuff, which is why the heap is one of the reasons why it's slower, is because it has this data structure that has to do all that stuff. Whereas the function call stack, the function call stack is here. It's nicely organized, right? So what happens? We call main. Oh, well, we just take the first empty location and we put all the metadata and variables there. We make another function call to foo. Great. We just take the next chunk of memory that's available and we put the variables and metadata in there. And then we call foo2 and we do the same thing again. And so it's all in a row. And here, I have a variable x, and in it is some garbage because I did not initialize it. And then, well, what happens when I return from foo2? Well, we just say, we have a pointer that's pointing to the top of the stack, and we just move the pointer. We say, okay, we're done with that. We call the destructor on anything that's in there, so if something needs to be deleted, it is deleted. Technically, mostly it just leaves it there, and then we overwrite it later, but you can think of it as being deleted, right? So when I come back from that, this gets deleted. I just really have to move a pointer. And then when I return from this function, same thing. And if I call another function, I put this back here. So there's never a gap in the stack. It's always very well organized, and that makes it fast, easy to keep track of, right? There's just need one pointer. Where's the end of it? And then, yeah, that's it. Questions? Okay. The heap, well, we talked a little bit about that. So if I want to declare something on the function call stack, so the heap. I think we went over that good enough, right? So in C++, we don't malloc anymore. We use new. And it's going to return a pointer. And instead of free, we use delete, right? And there's a good reason for that, because it works well with our classes. Now, technically, you could malloc. You'll get back a piece of memory. It won't be initialized, and you'll have to somehow figure out how to call the constructor on that. You might be able to call it directly, but I doubt it. I would have to think about how to do that in terms of syntax. But if you use an allocator, you can do it. An allocator is made to do stuff like that. It's maybe too advanced for us right now. So when we declare variables, we have statically allocated. If they're declared in a function, they go on the function call stack. We have dynamically allocated using the new keyword. These go on the heap, and then I get back the memory address of where they are. All right, and so for assignment 1, we're not even going to use dynamic memory if you like, but you don't have to. You can use all static memory just to keep things simple, right? And then so we'll learn a bunch of stuff about classes and everything else, and then later we'll get into dynamic memory and sort of how to manage it. I'm going to complicate things a little bit here. right? So statically allocated, you think, oh, function call stack, that's a good place to start. It's not quite the whole story, right? Because I can declare a class, as we will see, a class foo, and inside my class foo, I can statically allocate a variable. And what that means is that, well, so if I statically allocate a variable in a function, that variable is stored in the function call stack. If I statically allocate a variable in a class, that variable is stored with the class. So wherever the class is stored, that variable X is there. Maybe on the heap, maybe on the stack, but it's still, this is still statically allocated, even if this one is not. The X is always statically allocated. All right, so hopefully that makes sense. Questions? All right. Yeah, I'm really slow the last class. I'm not sure why. I don't know. I think I got excited about. Anyway, I got a little off topic last class, so we're gonna pull ahead of them a little bit, I think. All right, so structs and classes. So these are the aggregate variables. They're the same thing in C++. Okay, we are going to use classes because of what it implies about access. So the only difference between a struct and a class in C++ is the default access modifier, right? So we haven't talked about access modifiers, but you've seen them in Java, presumably. So a struct by default, everything is public, right? It's sort of like a C. It's a throwback to C. In C, everything's public. There's that you don't hide things. Nothing is hidden. Everything is public at all times. You just have to program carefully. So a struct, everything is public by default. You could still mark it as private or protected. This is considered bad software engineering. Well, it's considered bad encapsulation, right? So encapsulation is one of the things we're going to learn and how to use it and why it is useful. Classes, all members are by default private, right? Which sort of falls in line with the philosophy that we're going to be considering this semester, and that is this principle of least privilege, whereas we want to keep as much of the implementation details hidden from everyone else as possible, and only give you what you need to do the task that I'm providing for you, right? So any object, I have a set of public functions that you can use, and then everything else should be private. If you don't need it, I shouldn't show you it, right? This is going to allow us to change code a lot easier, and it's known as the principle of least privilege, which we'll be coming back to. The principle of least privilege is like a heuristic, right? It's like, well, should I make this thing private? Well, according to the principle of least privilege, yes, until proven otherwise. We can manipulate data using operators. So, oh yeah, you know what it was? I forgot all about. I forgot all about WooClap. That's why we were going so fast. All right, so let's do a little bit of review. I'm not sure. I tried a couple of different questions, and I'm not sure if they worked out very well, but we'll see. Wait a little bit for people to sign in. Let's see. So match the area of memory to its correct description. I'm not sure what will happen. The last section, I tried this and everything was already matched up. I didn't understand how this was even a question, but let's see what happens. Some of it should be kind of obvious. But... So this is, again, I haven't done this before, so I'm going to be figuring this out as I go. I guess this is who's answering what right now. And then we'll get to view the results at some point. String literals. All right, so just pretend I spelled that correctly. I really actually don't know how to look at the results. So most frequent answers. Okay. Code segment, users compiled code. Yeah, very good. Data segment, global variables and string literals. Yes. The heap, memory return from the system call, function call stack. Location variables, yeah. So function call stack, memory return from a system call. No, unfortunately, but that's good. I'm glad. Very cool. So we could talk about like memory return from a system call, function call stack. Again, when a system call is when I say system call, I mean a call to new or malloc, right? So yeah, maybe system call, maybe it could have been worded better. But the function call stack is memory that is allocated when I jump into a new function, and deallocated when I return from it. Whereas the heap is memory returned from a system call, a call to new or malloc. Local variables of a function memory address to return to, yeah. So this is the function call stack. And, all right, cool. So most of you are on the right track, and if not, that's okay. I know how difficult it can be to like, man, I was the worst. I was terrible at lectures. And somebody asked me today, what's the best way to learn? Should I take notes or should I do, I don't know, right? There's always that age-old question. Do I take notes and miss what's happening, or do I just not take notes and just passively try and take it in and then see if I remember? And it's like, there's no easy answer, which is one of the reasons why I videotape these. But what would the following expression evaluate to? So we just briefly looked at bed mass, right? So in C++, I guess this is we're tackling this a little bit early, but there are a bunch of operators we can use. There's a bunch of mathematical operators, but the order of operations is not necessarily left to right, right? So you have to consider, well, if I wrote this in C++, what would I get as an answer, right? This is an expression. This is valid C++ code. So what would be returned? Oh, 52%. Oh, all right, there we go. Yeah, so it looks like the fives have it. Fives are in the lead. And yeah, so order of operations in this case, well, bed mass, so brackets, exponents, division, multiplication. This, you know what, that's a good question. It evaluates the same in either case here. But I'm actually not sure if the division gets evaluated before the multiplication. So whether I do 3 times 4 divided by 2, I get 6. Or I'd say 3 times 4 divided by 2, which is 3 times 2, I also get 6, right? So which of those gets evaluated first? I'm actually not sure. How could I figure that out? I'm not sure. Maybe it doesn't even matter. But in this case, it doesn't matter. So this will give me 6, and then I have an expression 2 plus 6 minus 3, which I evaluate from left to right. So 2 plus 6 is 8, minus 3 gives us 5. So that is indeed the answer we would get. And I did actually run this just in case I made a dumb error, and it is 5, right? So bed mass, be aware. All right, so arithmetic operators, we have plus, minus, multiplication, division, plus, plus, minus, minus. So the increment and decrement, this is modulus, right? We have relational operators, Boolean operators. So comparison operators that return true or false. We have logical operators that combine Boolean expressions or Boolean values, right? So I could say if this is true or this is true, where or is this. Bitwise operations, which we're not really going to, I do not think we will touch on too much in this class. It's more of a C2401 thing. Assignment operator, so I can assign a value. I can do a plus equals, right? So A plus equals 5 takes the value of A and adds 5 to it. Functionally the same as this. And then I have the same for all of these other operations. All right. This might be maybe the one that you may have not seen before, right? So this is a conditional operator, so it acts sort of like a if then else, but it's an expression, so it always returns a value. So I would have, for instance, 3 equals A, and then I would say true or false, right? So it has to return a value. If it's true, it returns this value. So it returns a string with the word true in it. And if this is false, it returns this value, which is a string with the word false in it. And I can return numbers, anything that evaluates to a value. These are not blocks, right? So I cannot put a block of code in there. That will not work. Or at least I'm pretty sure. I've never seen it done. And I've always assumed it's true, but I've never actually tested it. So yeah, questions? You will see that here and there. Programming example, I don't think we need to look at that. Like there's nothing. Oh yeah, so here is the conditional operator, sort of same idea. But I think unless somebody has some question about what to do or what some of these mean, we'll probably try and skip some of this stuff. All right. So operators have characteristics. They have arity. This part is going to be important when we do operator overloading, right? So we can take these operators and make them work on our classes. And when we do that, we have to know things like the arity, which is the number of arguments that we send to that operator, right? So the plus operator is a binary operator because it has 2 operands. In this case, a 3 and a 5. Unary operator would be the plus plus. It has only 1 operand. Ternary, the only one that I know of is this one. Precedence, the order in what the operators execute, not simply left to right. We need bed mass, and associativity is the order in which operators of the same precedence execute, left to right or right to left. For example, if I run A divided by B divided by C divided by D, it goes from left to right. Does this one first, and then the result of that is divided by C, and then the result of that is divided by D. Whereas if I say A equals B equals C equals D, this gets evaluated from right to left. So this gets evaluated first, and then this gets evaluated, and then this gets evaluated. All right. Questions? Good. Putting data and operators together gives us expressions. So an expression is just something that evaluates to a value, right? So this, we can have functions as part of an expression as long as they return some value. Yeah, all of these are valid expressions. Expressions are typically embedded in statements. Expressions can be standalone statements also, right? So this is an expression. It's also a statement. This is technically an expression because it does return something, which we'll talk about. I mean, it returns v with the new value. This is a statement, but assuming it returns void, it's not an expression. All right. We have statements that control flow statements, right? So if, then else, the switch statements, do while, and for, break and continue. So we're going to use all those. This controls what happens with our code. All right, so blocks. So yeah. This is maybe the one thing that trips people up still is blocks. So a block in C++ is just the statements between an opening brace and a closing brace. So in this case, we have a block for a for loop. We have a block for, well, I don't have an if statement here, but if I had an if statement, it could have a block. In C++, I can have a block for no reason. And what these are, there's almost like little function calls in the sense that they have their own scope, their own environment, right? So if I run this code, what do we expect is the output here? So I'm going to declare a variable x equals 8, and then I'm going to run a for loop, and inside the for loop, I'm going to have this little block of code. Yep. 8, yes. And why is that? Yep. Exactly. So what happens is, well, I mean, again, it depends on the exact implementation, but let's say this is a function called foo. I have my function call stack, and inside is my variable x, and it is 8. And then I run this for loop, and in this for loop, well, I declare a new variable x, and this new variable x has a different scope, right? It is scoped into this inner block. And when I exit that inner block, that variable gets thrown away. Generally speaking, this would go, now again, it's implementation dependent, but generally speaking, it would go on top of the function call stack. And then when we're done, so you have some room to play with on the top of the function call stack to put these temporary variables. What about this one? So here I have a for loop, and then I have a block for no reason, where I declare this x and I print it out. I think it's pretty clear that that statement will return a 10, right? But what about this guy? This one's a little more complicated. But yeah. 9, yeah. So our for loop loops from 0 to 9. And it assigns the variable x, which is this variable here, the value. So let's say x starts as 8, and then I enter here, and it starts, it's so messy. It assigns it the value 0, and then 1, and then all the way up to 9, and then we're done. But I was able to access this x within the scope of this block, but it still existed when I exited because it was declared outside of it, right? Now I enter this new block. I can still, before I execute this, I can still access this x. Once I declare this new x, now I've shadowed that original x. And this might give you a compiler warning. I don't remember. Oh, it's almost end of class. It's end of class, right? But so yeah, what happens is that inside this block, I cannot access this x variable, right? It's hidden from me now because I have a new X, same name, different variable, which confuses the compiler. So yeah, then I would print out 9 here. So that's it for this class. Yeah, work on your tutorials, try and get your programming environment up and running. And next week, we are into the course.